Hi there, geometry students. It's Mr. Pouts, and I'm here with section 5.3, the video for section 5.3. I'm making this video on December 2nd, and it just so happens that December 2nd, which actually isn't a Tuesday, so I'll get rid of that, but December 2nd is Aaron Rodgers' birthday. So if you're a big Packer fan, you know who Aaron Rodgers is. If you're not, there's a good chance you probably also know who Aaron Rodgers is. But it's his birthday, so next time you see him, wish him a happy birthday for me. But anyway, section 5.3, writing down the goal, that would be right here. I can identify properties of perpendicular and angle bisectors. So we're going to do different things that have to do with perpendicular and angle bisectors, and we're going to have quite a few new vocabulary words as well. All right? So once you have that written down, I'm going to go on. Start us off with a couple of vocab words. The first one we're going to introduce you to is the word concurrent. And I'll put these into context in just a bit, but the definition, if you want to have this written down, concurrent means three or more lines intersecting at the same point. So if you have three or more lines intersecting at the same point, they are concurrent. All right? Next one is the point of concurrency. Well, if 3 points or 3 lines are concurrent, they intersect at the point of concurrency. So that would be the point where concurrent lines intersect. Pretty self-explanatory for that one. Next one, circumcenter and incenter. So these are two different terms we're going to talk about in this section, and they'll come up in the future as well. But the circumcenter of a triangle is the point of concurrency of the perpendicular bisectors. So if you have all the perpendicular bisectors of a triangle where they intersect, that is called the circumcenter. And since we're also talking about angle bisectors, the point where the angle bisectors are concurrent, where they intersect, would be the incenter. So that the incenter is the point of concurrency of the angle bisectors of a triangle. All right, make sure you have those all down, and we're going to put those into context and see how we can use those now. So, starting us off, this is something you need to know. It says for any triangle, certain sets of lines are always concurrent. Two of those sets of lines are the perpendicular bisectors of a triangle and the bisectors of the three angles. So when I say that, I mean if I'm taking each side and bisecting it, so that actually for this one it works out that it needs to bisect, so it needs to be a perpendicular bisector. They will intersect at the same point. And it just so happens in this case, I think this is equilateral, so the angle bisectors actually intersect at the same spot as well. They're almost identical here, but the angle bisectors and the perpendicular bisectors will intersect at the same point. So all three perpendicular bisectors will intersect at one point. All three angle bisectors will intersect at one point as well. You'll see it look differently on different triangles, though. So let's start us off with Theorem 5.6, and I'm going to pull this up so we have this out of the way. But add this to your theorem sheet, and just know that Theorem 5.6 is called the concurrency of perpendicular bisectors theorem. All right, so this theorem reads: the perpendicular bisectors of the sides of a triangle are concurrent at a point equidistant from the vertices. So we said that the perpendicular bisectors all intersect at one point, but that point, which in their diagram ABC right here, you see the three perpendicular bisectors intersect right there, they're also the same distance, so this would be the same distance as this, from the three vertices of the triangle. So that's unique. Another part of triangles being the strongest shape, their perpendicular bisectors intersect at the same point, being the same distance from the vertices. So if you're looking at over here in the symbols, it says perpendicular bisectors PX, PY, and PZ are concurrent at point P, and PA is congruent to PC, which is congruent to PB. All right, so if we look at that, let's go a little bit more into detail about perpendicular bisectors. The circumcenter is where the perpendicular bisectors intersect, we said. All right, so the circumcenter of, depending on the triangle, they can intersect inside the triangle, like we looked at the first two examples right here. A right triangle will actually intersect on the hypotenuse. So that's every right triangle, it'll intersect on the hypotenuse. And then an obtuse triangle, they'll actually intersect outside of the triangle, but they'll still be equidistant from each of the points. So that's going to be the same as that. It's going to be the same as that. So it's one. That's a unique thing from Theorem 5.6. All right, going on, the circumcenter. Let's fill in the blank here. The circumcenter is, we just said, from the theorem, equidistant from the three vertices and becomes the center of a circle. So if we were to make a circle, it becomes the center of a circle. The circle may be, and I think it says it like this in your notes, it may be inscribed or circumscribed. Inscribed. And we're going to use these terms more, not in this section, but inscribed would mean that that circle could be inside the circle, or inside the triangle. It could also be outside the triangle, depending on the location of the circumcenter. So like if you look at this one over to the far right, this is the center. The circle is going to go around this whole thing, and it's actually going to be circumscribed about the triangle. It's going to be on the outside of the triangle, but each of the vertices are on the outside of the triangle. So that's a unique thing there. Whereas, actually the right triangle would be the same way. But I think for this one, my circles don't look very good, but the triangle is all on the inside. Actually, for the right triangle and the acute triangle, the triangle is on the inside. Meaning, actually, they're all on the inside. Huh. Now, there is a way to show. Well, we're not going to worry about that right now. They could be also. Triangle could be. The circle could be inside of the triangle as well, depending on where it is. Going on, we're going to do two examples of finding the circumcenter. Remember, that's where the perpendicular bisectors intersect. So if you have a picture, I'm going to say if you have a picture, especially if it's a right triangle where the two sides are vertical and horizontal, draw the perpendicular bisector. So the bisector would be right here, and this side would go like that. Of the bottom one, it'd be right in the middle here. It would go up and down like that, the perpendicular bisector. And really, we already know they're going to all intersect here, so this one we don't have to worry about too much, but it will go right through this because of the slope of that line. So this is the intersecting point. A unique thing, though, is if you have two of the perpendicular bisectors intersecting, we know that the third one is also going to intersect at that same point. So when you have a graph like this one works out nicely. The point is actually, let's see, where's 0? So it's 1, that's 0.11 actually. Because this was the, that was the origin. Now you could do the same thing right here. If you have 0, 0, so I have just 3 coordinates, 0, 0, 0, 8, and 10, 8. Now you could graph it. And if it works out like this one, it might be nice if it's a right triangle. It won't always be a right triangle though. So this one we are going to use a different method. It's going to take us a lot longer to do it, but it'll work. So there's about 3 or 4 steps that we have to follow. You have to first find the midpoint of each one. And the reason I want to go through this is because we will have to do this. You'll have to do this probably once or twice this chapter. So now you know how to do it. So step 1, we're going to find the midpoints of each. So AB, the midpoints would be, we have the average of 0 and 0, the two x's divided by 2, and the two y's, these are supposed to be plus, sorry, divided by 2, it's going to be 0, 4. All right, let's do for BC. So 0, 10, and 8, 8. The midpoint, so that will be 5, and 16 divided by 2 will be 8, right? And then the last one would be AC. The midpoint, again, we're just finding the average of the x and the y, so that would be 0 plus 10 divided by 2, and 0 plus 8 divided by 2. So you'll have 5 and 4 for that one. So those are your three midpoints. Now step 2 is actually going to be finding the slopes of each line. Now technically, just so you know, we'll write that down, find the slopes. Technically, you only have to do it for 2, because I said if you have 2 of them and they intersect at one point, that's all you'd have to do. I'm going to do it for all 3 for right now, but you technically only have to do it for 2. So for AB we had here, I'm going to do then the slope. If the midpoint is this, the slope is going to be, if you look at AB, y2 over y1, so it's going to be minus y1, 8 minus 0 over 0 minus 0. Uh-oh. That is undefined. Can't divide by 0. So that means it's a vertical line. So B, let's look at BC. If the midpoint is right here, we're going to now find the slope. So BC, we have 8 minus 8 over 10 minus 0. So it's going to be 0 over 10, which is equal to 0. So we have the slope there. And the last one, the slope, is, we'll do 8 minus 0, because those are the two y's, and 10 minus 0. So it's actually going to reduce to 4 over 5. So there's the slope of that one. All right, we have our 3 midpoints, we have our 3 slopes. Now we got to take 2 of them and make equations for them. So we got to do at least 2. I'm just going to do 2. We're going to actually say write equations of lines perpendicular. So that was steps 1 and 2. Step 3, if we know the slope has to be, well, undefined, opposite of that would be a slope of 0. It has to go through 0.04. Let us plug in. So y into, let's do point slope form. So I just magically did step 3 for you. I plugged in the point for AB, the midpoint, and used the perpendicular slope, which would be 0, and I got y equals 4 as our equation. And I did the third one then. So I did these two, the perpendicular lines for those two. AC, I used the point 54, and I plugged in the slope of, oh, I did it wrong. You gotta plug in the perpendicular slope, remember? So, for this one, it'd actually be negative 5 over 4. That throws everything off then. So if you do negative 5 over 4, then we'd have y equals negative 5 over 4x, and that would be negative 25 over 4. So it'd be negative 6 and a fourth plus 4, so negative 10 and 1/4. Nope, negative 2 then. So negative 6 plus 4. So if you want to check the math, you can do that. I think that's correct. And then if that's our equation, our last step is to solve it. Solve that system. Because that'll tell us where the points intersect, or where the lines intersect. The point where they intersect. And if we have, and I can check my work, I might have made a mistake. But if we have the 2 lines, assuming these are the 2 lines, it's nice that we already have y equals 4, so we can plug that in for y. And we have, so this is step 4. we can plug it in for y. So we have 4 equals negative 5 over 4x minus, and we'll do minus 9/4. Because they're in fourths. So then we add 9/4 to both sides. So we have 16/4 plus 9/4. We have 25/4 equals negative 5/4 x. And do the inverse operation, which I'm going to do the reciprocal here. Multiply both sides by 4 over negative 5. Cancel this out. You get x is equal to, these will cancel out, negative 5. That works out nicely, but that's not it. We have the negative 5 as our x, and we already have the 4 as our y over here. So we have the point, negative 5, 4, will be our circumcenter. It's a lot of work to find the circumcenter with the given information. But I have the steps here for you. It's a lot of algebra, good review of algebra, just using those coordinates to find the circumcenter. All right, so take note of that, please. We will do more examples to help you out. I want to do one more thing before we're done here. It's Theorem 5.7, the concurrency of angle bisectors theorem. So very similar to the last one, but it says the bisectors of the angles of a triangle are concurrent at a point that is equidistant from the sides of the triangle. So if we bisect these angles, cut them exactly in half, we'll assume I'm doing this perfectly correct. They will intersect here, but that point would also be equidistant from the sides. So if we make up for this line here, this one here, and this one here, those lines, those blue lines would all be the same. Okay? And I don't have it labeled as they do on here, but we'll say that this is point P. So then if this is X, Y, and Z, those are all going to be the same lengths. Okay? So looking at just a couple examples real quick. Well, let's fill in the blanks first. The angle bisectors at the 3 vertices of a triangle intersect at one point. We said that. This point of concurrency is called the incenter. So I don't think we said that yet. That's the incenter. The incenter of the triangle will always lie inside the triangle. So hopefully that helps. Incenter would be inside the triangle. It's always going to be inside. We said the circumcenter could be outside sometimes, or on the circle, on the triangle. The incenter is equidistant from the sides of the triangle and becomes the center of an inscribed triangle. So the triangle has to be inscribed, or the circle, sorry, inscribed circle will be inside the triangle. All right? So just 2 examples real quick. Let's see if we can do them quickly. We said that by that theorem that all the, if this is the center of the triangle, that has to be equidistant from the sides. So this would have to be equal to this. So x would have to be equal to 14 in that case. That's easy enough. Same thing with this one. If we're assuming this is the incenter, because they are angle bisectors, then 2x minus 6 has to be equal to x plus 6. When we subtract x from both sides, you get x over here. You add 6 to both sides. It's going to be equal to 12. Okay, that's all we're going to get to from now. Again, pause it if you need to. Go back if you need to. We'll get to the rest in class. It's a lot to take in, so I want you to just process it, see what you can understand, see what you have questions, and if you have questions, especially with this goal that we're dealing with, please write them down and ask when you come to class. Otherwise, we'll see you next time.